So welcome again. This will be the third lecture of our quantum programming workshop, QBronze. I hope all is going fine. Do you have any questions about the previous notebooks, about homework? I mean, like something technical. So you can always write in this code if you have any questions. Um, So today, we will cover those notebooks. So we have two qubits, phase kickback, entanglement, spurious coding, and quantum teleportation. So two qubits will be mostly like the quantum version of what we did on Monday with multiple probabilistic bits. So you will be really familiar to this concept. And then we will see some concepts which are not really existing in the classical side, but they are like more special to the quantum systems. Okay, if you don't have any questions, then I will start. And when I'm talking, if you have any question, you can write it in Q&A in Zoom. And sometimes I also ask some questions, and then you can type in chat. This way it will be easier to track the questions. Okay, let's start. So if you remember when we had multiple probabilistic bits, say we have like two probabilistic bits, then we could identify four different states, like 0, 0, 0, 1, 1, 0, and 1, 1. And the same here will be for qubits. So if you have two qubits, then if they are either in state 0 or in state 1, again, there are like four possibilities: 0, 0, 0, 1, 1, 0, and 1, 1. And we show this as cat 0, 0, cat 0, 1, cat 1, 0, and cat 1, 1. And in this case, how to read this? So 0, 0 means first qubit is in state 0, and second qubit is in state 0 as well. But like for 0, 1, so this means first qubit is in state 0, and I was thinking about Qiskit, but okay, right now when I say first, it's just I am reading it from left to right. So the first qubit is in state 0, and second qubit is in state 1. And in short, like actually this is cat 0 concatenated with cat 0, or cat 0 concatenated with cat 1. But to write this in short, we remove this those symbols in between, and this is how we express it. But this is how you should read this. But of course, a quantum state, a qubit does not have to be always in state 0 or state 1. It can be in any arbitrary quantum state. So we will see how this will look like. Or maybe I can, so here we have a more. I can shortly show it here. Say I have a quantum state. So this is alpha 0 plus beta 1. And let's say I have another quantum state. And this is A0 plus B1. So our quantum states does not have to be only in state 0 or only in state 1. It can be arbitrary. And in such a case, the combined state of the two qubits again will be really similar to what we did for classical systems. We will take the tensor product. And then we have like 0, 0, and there will be some amplitude here, plus 0, 1, plus 1, 0, plus 1, 1. So the two qubits can be in any linear combination of those four states. Can you tell me what should come here as the amplitude of 0, 0? Um, I didn't give any numbers, be careful. I didn't say alpha is equal to 1 over square root 2 or beta is equal to 1 over square root 2. Okay, there are some answers, a plus b, alpha plus a. Let me ask you something different. What is the probability that I will observe a 0 if I make a measurement for the first qubit? What is the probability of obtaining a 0 for the first one? I have this qubit in state alpha 0 plus beta 1, and I'm making a measurement, and I'm asking what is the probability that I will observe a 0 state. Okay, there is alpha module square. Any other answers? Feel free to write. It can be wrong, it's not important. Alpha. Let's make it more concrete. Let's say this is my quantum state. 1 over square root 3. That's 0 plus square root 2 over 3. That's 1. In this case, by the way, there are some correct answers, but I want more people to understand what's going on. So imagine that this is my qubit state. 1 over square root 3, 0 plus square root 2 over 3, 1. So this is a 1, sorry. What is the probability of observing 0 in this particular example here? What is the probability to get a 0? It's 1 over 3, right? So first of all, so don't confuse like the Hadamard state, the state that when you get after applying Hadamard, you don't always need to get 1 over 2. So it is just a particular state. But the example I just gave, it is also a quantum state. And in this particular example, probability of getting 0 is 1 over 3. And probability of getting 1 is 2 over 3. And how do we find this? We square the amplitude. So 1 over square root 3 is the amplitude. Since it's a real number, I don't need to get the modulus here. But in general, it can be complex number. But throughout this tutorial, we will only work with real numbers. So I just get the square of it. And the probability is 1 over 3. Any questions about this? Is it clear? Yes, exactly. Coefficients are amplitudes and the probability is a square. Then, going back to this question, I asked you the probability of obtaining a 0. So the answer is alpha squared. Now, is this clear? Now I am asking the same for the second qubit. What is the probability of observing a zero for the second qubit? I see an answer, a square. Any other answers? Yes, it's a square. I hope this is clear for everyone. But if you have any doubts, please write. So, the probability of observing zero for the first qubit is alpha square. The probability of observing zero for the second qubit is a square. Now, the question is, what is the probability of observing state 0, 0? This means both the first and the second qubit, they should be in state 0. What is the probability? Okay, alpha square a square. Are there any other answers? You can also put this reaction to the answer. One of you did. This also makes sense. If you like, if you are lazy to write it, you can also put the reaction. And yes, the answer is correct. The probability will be alpha square times a square. Now I am going back to my first question. And what should be this amplitude? If I write the combined state, what should be this amplitude? Okay, there's an answer, alpha times A. Any other answers? Or do you agree? So the answer is right. This is alpha times A. And how you obtain this? So remember the probabilistic bits. And remember the tensor product. It's exactly the same idea. You should get the tensor product of qubit 1 and qubit 2. And in this case, this is like multiplication over addition. So you take this and multiply it with this one. And when you multiply this, you obtain alpha times A. And those two states get concatenated, so it's 0, 0. Can you tell me amplitude for next one, 0, 1? What should be the amplitude? Yes, be careful about plus. It's not plus. It's alpha times B. Exactly. I think you got the idea. Uh, so this is just tensor product of two qubits. I use state representation. You would get exactly the same answers if you had used vector representation. Remember, we could also do tensor product on vectors. So this is how you write combined state of two qubits in general. And if you have two qubits, the state of your system will be a linear combination of those four basis states, 0, 0, 0, 1, 1, 0, and 1, 1. Any questions? I will delete what I have written so far. Okay, now let's move on. Here you see the vector representation for state 0, 0, 0, 1, 1, 0, and 1, 1. And you can go back and check. They are the same as the ones we had in probabilistic systems. And how you get this? Basically, you can do the tensor product of 1, 0 with 1, 0 to get 1, 0, 0, 0, and so on. And this can be generalized to k qubits, actually. So not only 2, but you could have like k qubits or k bits. In this case, what would be the size of your vector? Say I have k qubits. How many entries do I need in the vector representation? You see it? For instance, this is for 2, and our vectors have size 4. Okay, let me repeat. So in this example, we have 2 qubits, and we need a vector with 4 entries to represent this quantum state. Now I am asking, suppose that we have k qubits. What will be the size of our vector to represent a system with k qubits? Yes, there are some answers, 2 to the k, 2 to the n, like, same. And how can we see this? When you have 2 qubits, uh, you have 4 different basis states: 0, 0, 0, 1, 1, 0, and 1, 1. And as we did above, um, any like the system can be in any linear combination of those 4 basis states. So a system with 2 qubits, we need like a vector with 4 entries to represent it. And those 4 entries will correspond to amplitudes of 0, 0, 0, 1, 1, 0, and 1, 1. In the example we had, it looked like this: alpha A, alpha B. I guess it should be beta A and beta B. And if you have k qubits, then you can have 2 to the k different possible states. And in this case, your vector, it should be of size 2 to the k. It should have 2 to the k entries. For instance, if this was 8, then think about it. You would have like 0, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, and 1, 0, 0, 1, 0, 1, and so on. And also think about the binary representations. Those are states 0, 1, 2, and 3. And if we had 3 qubits, we would have 8 different states, and we would go up to like 4, 5, 6, 7. So there is also this correspondence. Now, do you have any questions, or is this clear? And from this, you can readily see that to simulate a quantum system, you need exponentially many classical resources. Why? Because suppose you have a quantum computer with n qubits. To simulate the behavior of this quantum computer using a classical computer, you need to make operations with matrices or vectors of size 2 to the n. For instance, using your laptops, you wouldn't be able to run in Qiskit quantum circuits maybe larger than, I don't know, like 14 qubits. This depends on your computer's like RAM. But if you try, possibly, like if you are using an ordinary laptop, if you try constructing a quantum circuit in Qiskit, say with 20 qubits, then I think you will have trouble. Why? Because in the background, what you have is like a vector to represent all possible states those 20 qubits can be in. And as I mentioned on Monday, we are working with simulators. So we are simulating the quantum system. So we are simulating a system with 20 qubits, means that we have 2 to the 20 different possible states, and we need to store all the amplitude information using a vector of size 2 to the 20. 2 to the 20. So this was just a side information, but I wanted to mention this here. Next, we will move on to operators on multiple qubits. This is not something we did for probabilistic systems. We could do it, but like we omitted there. So we have seen like single qubit operations, like Adamar or NOT gate, for instance, and those were represented by 2 by 2 matrices. And those are acting on a single qubit, which is represented by a vector of size 2. But now, suppose that we have 2 qubits, and suppose that we are applying Adamar on each of them. Now, the question is, what is the operator that is applied on the system? So, if you think about each qubit individually, if they're initially in state 0, then what you have is the first one is in state 1, 0, and the second one is in state 1, 0. And for instance, to write the new state of the system, what you could do is the following. You could apply Hadamard to this and Hadamard to this one, get the results, and then take the tensor product to write the resulting state. But what is the operator I should apply to this state to get the same result? Because this is the same state. If I have 2 qubits which are initially in state 0, then this is how I represent the current state of the system. Because this is state 0, 0. And the operator that corresponds to applying Hadamard on both qubits is this one. Now, when I moved on, I will show you like how you can see this in different ways. But this matrix is just the tensor product of those 2 matrices. And how you get tensor product of matrices? You get this entry, multiply it with this matrix, and it's here. And then you take this entry here, multiply with this matrix to get this part. And so on. And you see like the only difference is here because this is with minus. So we have minus signs here. Before talking about unitary backend, I would like to show you this to make this more concrete. So we will see 3 different ways to find what happens if we apply Hadamard on 2 qubits. So this is the first way. So this 1, 0, 0, this is state 0, 0. This is a state of a system with 2 qubits, and this is the operator corresponding to applying Hadamard on 2 qubits. We represent it by like this, with this tensor 2. And this is the resulting state. And what happens conceptually if we apply Hadamard to 2 qubits? You get equal superposition of all 4 states. So 1 over 2, 0, 0, 1 over 2, 1, 0, 1, 1 over 2, 1, 0, and 1 over 2, 1, 1. And this is saying us we can observe 0, 0 with probability 1 over 4, 0, 1 with probability 1 over 4, and so on. All those states have equal probability. So this is what Hadamard gate is doing. If you apply it to all qubits, then you get an equal superposition of all states. And this is the first way to see this. And this is the second way, the way I mentioned at the beginning. I apply Hadamard to first qubit, I apply Hadamard to second qubit, and those are the resulting states. Then I take the tensor product of those 2 resulting states, and I get the same result, which is expected. And finally, You could use state representation here. Now let's check what's going on. We apply Lamar to first qubit, and this is the new state, 1 over square root 2, 0 plus 1 over square root 2, 1. And we have the same thing here. So the only difference is between the previous one is it was using this vector representation, and now I'm using state representation. And just I use tensor product to distribute this over the second one. And we have 1 over square root 2 times 1 over square root 2, so 1 over 2, 0, 0, plus 1 over 2, 0, 1, and so on. And again, I have the same output. So those are different ways you can see this, why this is correct. Do you have any questions? No questions? Okay. I hope it is understood. This is why you don't have any questions. Um, and here we talk about unitary simulator. Uh, so far we were using the simulator which was giving us statistics, like counts. Remember, we were giving some number of shots, and based on this, it was giving us some statistics. Say if we have 1,000 shots, then we were getting something like, okay, like 500 times 0 and 500 times 1, something like this. But there is another option in Qiskit, which is called the unitary simulator. And unitary simulator returns you the unitary that is applied on the quantum system so far. So imagine you apply a bunch of gates on the system. I don't know, like it can be X, H, any gate you like. And your system can be of any size. It doesn't matter. And by using this unitary simulator, you can get the unitary that has been applied so far on the system. Just product of all the things you have applied. Now let's check. And since we have applied two Adamars here on this quantum circuit, um, when we run the unitary, I don't know what's the problem, but I can try printing current unitary. Probably my Qiskit version is old. Okay, I'm not sure right now because I remember, I think it's related to my Qiskit version. This might not be working anymore. Yes, okay, I should use data. Okay. Um, okay, this is the unitary as a result of applying two Adamars on the quantum system. And you can check that it is the same as this matrix we have found here. But of course, so in this particular example, since we applied Adamar on both qubits, it didn't matter. But in general, you should be careful about order of qubits. Uh, Let me ask you one question. If we apply only 0, sorry, if we apply Adamar only on qubit 0, but not on qubit 1, and we have a system with 2 qubits, how can I find the matrix that is affecting the whole system? What would be the corresponding operator? So In the case when I am applying Adamar on both qubits, the corresponding operator is Adamar tensor Adamar. What? My question is the following. Suppose that I am applying Adamar only on qubit number 0, and I am not applying anything on qubit number 1. What is the corresponding operator that is applied on the system? Adamar tensor identity, not operator. Okay. There are different answers. Nice. We can discuss. Discussing wrong answers is really important because probably there are some other people who are thinking in the same way, and understanding why something is wrong, I think it is better than understanding why something is correct, because you also see the other case, why something cannot be true. Okay, let me wait a bit more. Maybe there might be some other answers. Okay, now let's discuss the answers. So first of all, the correct answer should be identity tensor Adamar if we are obeying the Qiskit order. Why? Because according to Qiskit, we should think in terms of Q1, Q0, and on Q1, we are not applying anything, so this is identity. And on Q0, we are applying Adamar. Therefore, if you check with the unitary backend, the resulting matrix will be identity tensor by Adamar. And you can see this here. So since identity is 1001, in this block you see exactly Adamar. In this block you see a 0. In this block you see a 0. And in this block you see again Adamar. Now about the other answers. So not operator. So first of all, not operator is 2 by 2. So therefore, the result cannot be not operator because the result should be something which is 4 by 4, as it is applied on a system with 2 qubits. And like not operator is making 0, 1 and 1 into a 0. So it's not. Writing it as ket1 tensor Adamar, this is not exactly correct because ket1 state and identity operator, they are two different things. Ket1 is a state, but identity is an operator. So don't like mix the two. So if you are saying it is like as if Adamar is applied on state 1, so it's still not correct because as I said, like your answer should be 4 by 4. And ket1 is not the same thing as identity. And like other answers are correct. So in this case, it's not h times I, it's I times h. They're different. Let me show you h times identity. If we had applied Adamar on qubit number 1, then this is now h times h tensor identity. So it's different. Any questions? And it will be like, suppose that I'm applying x on 0, then the unitary applied on the system will be Adamar tensor x. See, like, think, diagonal switched because this is adamlar tensor X. Any questions? Okay. Let's move on to CNOT. This is one of the most important operators you are going to learn about. And this is an operator which is applied on two qubits. So unlike H and X, which you have seen so far, this is different. And this is the matrix representation for CNOT operator. And actually, how you should read this matrix representation is as follows. You should think, so remember table representation. We had inputs, we had outputs. And for instance, for, I don't know, identity or not, we had single qubit and we had two states. Therefore, our states were 0, 1, 0, 1. This time we have 0, 0, 0, 1. Let me just type this. It will look better. 0, 0, 0, 1, 1, 0, and 1, 1. Ah, okay, one is at in the next line, but you get the idea. And here on the left, this is what we have. 0, 0, 0, 1, 1, 0, 1, 1. And now, if you see a 1 like this means 0, 0 is mapped to 0, 0. 0, 1 is mapped to 0, 1. Now, there is something here. 1, 0 is mapped to 1, 1 here. And 1, 1 is mapped to 1, 0 here. So this is how CNOT is acting on two qubits. If your input is 0, 0 or 0, 1, then it's not changed. But if it is 1, 0 or 1, 1, then what happens is 1, 0 is mapped to 1, 1 and 1, 1 is mapped to 1, 0. And actually the CNOT name comes from controlled knots. And what is like the control? So it is applying a knot on the second qubit if the first qubit is 1. So that's how CNOT works. Check here. If the first qubit is 0, then nothing is happening on the second qubit. It's not changing. But if the first qubit is 1, then the second qubit is changing to, then not is applied on the second qubit. Any questions? And CNOT is kind of implementing an if statement in quantum circuits because here in quantum circuits, we don't have something like if because we cannot read the state of any input. We cannot say if this qubit is 0, do this. If this qubit is 1, do this. But instead we have those controlled operations which kind of help us to do such things. So we can now say, okay, if it is a 1, then implement a not. Um, the, the qubit which is controlled is called the control qubit. And the qubit on which NOT gate is applied is called the target qubit. Right now, we have assumed that qubit 0 is the control and qubit 1 is the target, but you can apply CNOT between any pair of qubits in a quantum circuit. It can be that your control is qubit number 5 and your target is qubit number 2. In such a case, of course, your matrix representation would change. But like this is the matrix representation when you have two qubits and when the first is the control and second is the target. And in Qiskit, the way to implement this is to use CX gates. And it takes as parameter two integers. First one is the control, and second one is the target. Um, and here we will just show the outputs. What will happen? We will try to see what will happen for all possible input states. So this is what we represent by pairs. So we will try applying C naught on 0, 0, 0, 1, 1, 0, and 1, 1. And to initialize our quantum circuit in such state, say we would like to start from 0, 1, then we will initialize our quantum system so that it is initially 0, 1. And this is what the code is doing here. I know this might be confusing at the beginning, but this is to obey Qiskit order. And what this is doing is the following. Let's take 0, 1. And if it is checking index 1. So index 1 of 0, 1 is 1. And therefore, it is applying not on qubit number 0. Why? Because according to Qiskit's order, if this is the state you would like to obtain, then this is qubit number 0, and this is qubit number 1. So to obtain quantum state 0, 0, 0, 1, I need to apply not on qubit number 0. And this is what those 4 lines is doing here. It's checking the input, and according to the input, it's preparing the state. And then we apply a C naught. And why we are doing like C naught 1, 0? Because we would like to see the exact behavior we are expecting, so that we are not affected by Qiskit's order. So this is the control, and this is the target. So therefore, here we provide 1 as the control and 0 as the target. So control and target. Now let me run this and let's interpret the results. So if the input is 0, 0, and if we apply a C naught, then there is nothing happening in the output. You still get 0, 0. And if the input, by input, I mean the state we prepared, by the way, like this is the input, and this part is preparing the input. So this is the input 0, 1, and we are getting 0, 1. Nothing is happening again. But now, if the input is 1, 0, see here we have a not. So this becomes a 1. Now this is 1, 0. And if we apply C naught, then the output is 1, 1. And similarly, if the input is 1, 1, then the output is 1, 0. So whenever the controlled qubits, so this is how we show this in a circuit. Controlled is shown with this dot, and not is shown by this plus inside the dot. And whenever the control is 1, then not is applied on the target. Any questions? Now, suppose that this is your quantum state. It's A00 plus B01 plus C10 plus D11. What happens if we apply a C naught, where first qubit is the control and second qubit is the target? It's not always the case that we will apply C naught to only basis states like 00 or 01. We can apply it to a state in superposition, so don't forget about this. And what is your guess? What will happen if we apply C naught to such a state which is in superposition of all four states with amplitudes A, B, C, D respectively? Any ideas? One, 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 zero. Okay, so it will be A00, B01, C11, D10. Okay, we have, I think the Betül's answer is also, I think, saying the same thing. Any other answers? A00, B01, D10. Okay, it's the same. And yes, the answers are correct. So you should think about this as a linear system. Therefore, when you are applying C naught, it's like you are applying C naught to this part, this part, this part, and this part. So this is a state in superposition. And when you apply C naught, this will stay as it is. Also, this will stay as it is. But here, this will change to 1, 1. So it's a C11. And this will become D10. If you think about vector representation, what you have is the following: A, B, C, and D. And think about now the matrix of C naught here. And this is just swapping the last two rows. So this becomes A, B, D, C. And this is exactly what we have. So this becomes D, and this becomes C. So D is the new amplitude of 1, 0, and C is the new amplitude of 1, 1. And there is no difference in writing C11 plus D10 or D10 plus C11. So it doesn't matter. But as the matrix representation, this is what you would have. So again, there are two different ways you can see this. You can see this either through vector representation, or you can do this through this state representation. Any questions? Okay, then I am moving to phase kickback. Um, so here, there is a task you should do. But I will show you this through mathematical derivation, what's going on. So here, you start in quantum state 0, 1. And then you apply C naught operate. So you apply different than what we did previously. You first apply Adamar on both qubits. And then you apply C naught operator. where Q1 is the control and Q0 is the target, and you apply Adamar again. And as a result of this, what you will observe is that output will be the state 1, 1. This may seem odd. We are applying a C naught where this control and this is target, and or just a second, let me think. Will the output be 1, 1, or actually I think it will be 0, 0. Let's run the circuit to make sure. Oh, okay, it's 1, 1. Okay, it's 1, 1. I am correct. Okay. Okay, I mixed the casket order again. Sorry. Okay. So Q1 is the control and Q0 is the target. So this means this is the control and this is the target. Second one is the target. But as a result of this, you will observe that the output state is 1, 1. This is not intuitive because we are applying a control knot where this is control, but the control is kind of changing at the end. Why this is happening? This is happening because we have other marks in between. Now we will see mathematically why this is happening. The reason behind is something called phase kickback. I will tell you about this at the very end, but now let's just observe what's happening mathematically. Let's trace this. This is also useful to get used to those mathematical expressions and so on. Okay, so we have a quantum system in state 0, 1. And then we apply Adamar on both qubits. So we apply Adamar on 0 and Adamar on 1. So this is the, so let's write here to not forget. This is our initial state. And this is Q1. And this is Q0. So we apply Adamar on this, and this is what we get. This is also called the plus state. So this is a system of, this is the state of the first qubit. And we apply Adamar on this one, and this is the state we get, and this is the state of the second qubit. So this is the state of the composite system. It's this plus state. So this is what it is called, tensored by the minus state. Those are the states you get after applying Adamar to 0 and 1 states. Do you have any question until here? Is everyone okay that this is the new state of the quantum system after applying Adamar? Any questions here? Okay, then I'm moving down. Now let's just express this again so that we can apply C naught easier. I am just here moving from here to here. We are just distributing this like it's 1 over square root to 0 tensor this state plus 1 over square root to cat 1 tensor this state. Is this part okay? You could go on and just multiply everything so you would get 1 over 2, 0, 0 minus 1 over 2, 0, 1 plus 1 over 2, 1, 0 minus 1 over 2, 1, 1. Is this part okay? So please let me know if I need to repeat something. Okay, then now we applied Adamars. Now we are going to apply this C naught. So This is the control, Q1 is the control, and Q0 is the target. Now be careful here about what is control and what is the target. Because, so here you have plus in between. And this is Q1. This is Q0. And again, this is Q1. And this is Q0. So since we're applying C naught, where Q1 is the control, and since this is 0, this is not changed at all, this part. But in this part, Q1 stays as it is, and we are applying a not here. So this 0 becomes a 1, and this 1 becomes a 0. Why? Because we're applying a not on this quantum state. Any questions here? How did we say Q1 and Q0? So this is how we started, remember. We had state 0, 1, and to use Kiskit's ordering, we said this is Q1 and this is Q0. And we said we are going to apply C naught where Q1 is the control, Q0 is the target. This is what we said at the beginning. First, we apply Adamar on both qubits. And then we apply C naught where this is control and this is target. Now, we will just move the minus sign outside. This is done moving from this step to this step. Now let's check. This is minus 1 over square root to 1 times 1 over square root to 0, which is minus 1, 0. Check, it is the same here, minus 1, 0. And we have like minus 1 and minus 1, so this is plus 1, 1. And it's the same. We just moved minus sign outside. Is this okay? Now, we are going to apply Adam's back to each qubit. Remember, let's check what is written here. Apply C naught operator and apply Adamar to both qubits. Okay. Now, okay, we were here. You can see that this state is equal to this state. Why? Because they have this part in common. The second qubit is like it's the same. So you can just rewrite it like this. You can just check. This is 1 over square root to 0 multiplied by this and minus 1 over square root to 1 multiplied by this. So they are the same. And now, if you apply Adamar on both qubits, you should first remember the following. If we apply Adamar to 0 state, then we get plus state. And if we apply Adamar back to plus state, do you know what we get? So it is like if we are applying Adamar twice. What do we get? Zero, right? Because if we apply Adamar twice, this is just applying identity. And you go back. You get again 0. Likewise, if you apply Adamar to state 1, then you get minus state, which is the state here. And now we are applying Adamar again. What will be the output? Let me remind you what we did so far. We were tracing the system. We started with 0, 1. We apply Adamar to both. Then we applied C naught. Then we apply Adamar again. So this is the last step. So after C naught, this is what we had. This quantum state at the bottom. This is what we have after the application of C naught. Now I want to know what happens if I apply Adamar on both of them. This is the question. I'm applying Adamar on this quantum state at the bottom onto the system with those 2 qubits. What will be my output? Okay, I see some answers, 1, 1, and 1. Any other answers, or is something not clear? Maybe you couldn't follow. That's really normal. Okay, nice. Yes, that's correct. If you apply Adamar to minus state, then you get 1, of course. And since we have 2 minus states here, if we apply Adamar, then we get 1, 1 as a result. So what happened? We started with 0, 1. Let's go back. We started with 0, 1. We apply Adamar to both qubits. We apply C naught, where Q1 is control and Q0 is target. We apply Adamar again, and the result was 1, 1. So it is as if C naught worked in the reverse direction, right? So we had like something strange. So controller qubit was affected as a result of the NOT application because of our construction, basically. Though, because we had those other marks in between. So what's going on here and why this notebook is titled Phase Kickback? So what's happening here actually is the following. Think about this state, this minus state, which is the state when you state you obtain if you apply Adamar to cat1, and this is 1 over square root to 0 minus 1 over square root to 1. Okay, now the question is, what happens if you apply and not on the state? What is the result if I apply not on this quantum state? Will it be the same? There are 2 different answers. Any other answers? Or do you agree with them? Okay, let's try to see what happens. We have 1 over square root to 1. And we have cat1 here. Why? Because we are applying a not, so 0 becomes a 1. I have the minus. Then I have 1 over square root 2, and this 1 becomes a 0. And now, if you just take minus outside, you will have exactly the state here. 1 over square root 2 gets 0 minus 1 over square root 2 get 1. So can everybody see this? Please ask if you have any questions. So thank you, Betül. Our others are also following, so please let me know. Or if you want me to repeat something here, I can repeat. What I did was, I started with minus state, which is 1 over square root 2, 0, minus 1 over square root 2 ket 1. Then I applied a NOT gate. And what is the impact of NOT gate? NOT gate turns 0 into a 1 and 1 into a 0. So therefore, this was the state I got. 1 over square root 2, 1, minus 1 over square root 2, 0. And then I just took the minus outside. So this becomes 1 over square root 2, 0, minus 1 over square root 2, 1. And this is exactly the state I started with. So from this, I can conclude that if I apply NOT gate on minus state, then what I get is again minus state with a minus at the beginning. So you can also think about this as minus 1 times minus state. So you can think of this as minus 1 if you want. And actually this is called the phase. So if you know, so this part is not important if you don't know about it, but if you know about eigenvectors, then you can see that this minus state is an eigenvector of the NOT operator with eigenvalue minus 1. And this is what is happening in this example. If you apply NOT gate on minus state, then you again get the minus state with a minus sign in front. And this is what is called the phase. And this is what kickback means. It's kickback. And how this affected our results? Because in this example, when applying C naught here, remember, we were applying C naught at this stage here, between this and this. And when we applied C naught, we had the sign here, which was changed. And this was a result of phase kickback. Why? Because here we have a minus state. And because this was a 1 and we were applying a C naught, we applied a naught on this minus state. And this became minus. This kicked back the minus 1 sign in front. And this is why we had this minus here in between. And then this resulted after applying Adamar in the state 1, 1, and so on. But this is really what phase kickback is, this minus 1 appearing in front. And this was just to give you another idea about what can happen when you work with quantum states. So yes, C naught is changing the target, but if you put some other Mars in between, this might not be always the case because something called phase kickback might happen in between. In this notebook, we also see like how we can modify the states. There is a question, how does affect Q1 to change state? So the reason is, since we applied other marks in between, because of this minus sign appearing here, the first quantum state changed from plus to minus. So actually this is what is happening in short. We start in state 0, 1. Then we apply Adamar to get plus and minus states. So we apply Adamar here. Then we apply C naught here. And applying C naught changes this into minus minus. So that when we apply Adamar back, this becomes state 1, 1. So C naught, if you apply this on our usual basis states like 0, 0, 0, 1, 1, 0, 1, 1, then yes, it's not affecting the control, but it's affecting the target. But because of the space kickback effect, when you apply this on quantum state plus minus, then it's keeping the target, but it's changing the control as it is in this example. You don't need to like memorize this or learn this. What happens when I apply C naught on minus state, etc. All you need to know is what happens when you apply C naught on 0, 0, 0, 1, 1, 0, and 1, 1. But this is the reasoning behind this minus sign, which appears here as a result of C naught application. Why? Because this minus 1 is the eigenvalue of this naught vector, as I explained. And because of this minus sign, this plus state is becoming a minus state. And after applying Adamar, this is becoming a 1. So that's all what is happening. This was just an example, exactly. Why we started with 0, 1, this was just an example. And we started with 0, 1 to see this effect. Because this, so this not applied on minus state gives you the minus 1, which appeared as the phase. And to start with this minus state, this is why we started with 1, so that after applying Adamar, we got this minus state. If we had started with 0, 0, then we wouldn't see this. Nothing would happen, for instance. Because if we apply, by the way, this is the other eigenvector. If we apply not on plus state, then you get not again. Sorry, plus state again. You can check this. It's just 1 over square root to 0 plus 1 over square root to 1. And if we apply not, nothing changes. Do you have any questions? Okay, I think everyone is tired. Let's give a break. Let's start at 25. So 15:25. I'm also writing in chat. So we have a 12-minute break. So see you at 15:25. Hello again. We are back and we will switch to a new topic and which is really something important, which might you have heard about. But before moving on, do you have any questions? So today we have seen how to work with multiple qubits. And actually this is important because again, we will be working with multiple qubits in this notebook and the following notebook. We have seen how to represent our multiple qubit states, how to modify them through operators, and we have seen something called phase kickback. Um, it's not, so don't worry if you didn't get it fully, but it's important to understand basic concepts, how we are modifying the state, what's happening to the state when we apply some operator, and so on. And in this notebook, we will talk about, to start with entanglement, which is one of the most important concepts about quantum physics and quantum computing. The first one is superposition, I think, and the second is entanglement because this is what is really different than classical computing. Those are things which we don't have in classical computing and which we expect to see some benefit in using uh, quantum computing. Question, can you sketch up the unit circle with plus, minus, plus, minus? Okay, let me shortly do this before we move on then. So if we are working on the 2D plane, so this is state 0, and this is state 1, and this is minus 0, and this is minus 1, and this is plus. Why? Because this is 1 over square root 2, 0 plus 1 over square root 2, 1. And this should be the minus state. Why? Because this is 1 over square root 2, 0 minus 1 over square root 2, 1. And what else? Minus 0, minus 1. So this should be uh, minus plus. And this should be minus, minus. You're welcome. And I guess you were the one asking about reflection of and not operator. And actually, this was correct. So, not operator is a reflection about the axis y equals x. So, for instance, if you think about plus state, it doesn't have any impact. It's just staying there. But if we apply it on this one, minus state, then it is reflected to here. Okay, let me delete. And let's start with entanglement. Um, so this concept also, you might heard the famous quote by Einstein, spooky action at a distance. This is what Einstein called entanglement. So now let's start with the mathematics and then let's try to understand what's happening. Suppose that we have two qubits and say the first one, so Asya has the first one and Boris has the second one. Uh, so we are applying Adamar to the Asya's qubit, and Asya's qubit now becomes 1 over square root 2, 1 over square root 2. And we can also express the combined state of the two qubits like this. So this is the Asya's qubit, 1 over square root 2, 1 over square root 2, and 1, 0. This is qubit of Balbis. And now we are applying a CNOT between those two qubits. And we can do this through matrix operation, right? So this is the current state of the vector. And if we apply this matrix operation, remember this will just swap third and the fourth row. So our new state becomes this one. 1 over square root 2, 0, 0, 1 over square root 2. Another way to see this is the following. Initially, this is what you have as the first qubit. And this is what we have for the second qubit. And if you combine this, this is what you have. 0, 0 plus 1, 0 over square root 2. And now we're applying a C naught. So this will not be affected, but this will be affected. So this becomes 0, 0 plus 1, 1. And this is the same thing here. Any questions until now? So please ask if you didn't get any step here. Okay, if you don't have any questions, let me ask you a question. Now, suppose that we measure the first qubit. Asya measures the first qubit. And let's say she observes that it is 0. Now, suppose that Bob is also making a measurement. What will be the measurement result of Balbus? Can we say something about this? Okay, let me repeat the question. By the way, Yavuz, if you can write exactly what you didn't get, I can explain. So we applied Adamar and C naught. Okay, like Asya Babis has 2 qubits. And finally, they have this quantum state. The qubits of their qubits has this quantum state. 1 over square root 2, 0, 0 plus 1 over square root 2, 1, 1. Now, here's the question. Asya is making a measurement. I mean, like the first qubit is measured, and Asya observes that it is a 0. Can you say anything about Balvis qubit? If Balvis makes a measurement, what is he going to observe? Will he observe 0? Will he observe 1? Or will he observe 0 and 1 with equal probability? What do you think? So, question is, Asya observe 0. What can Balvis observe? Meanwhile, let me explain the C naught part at the end again. So here we have quantum state 0, 0 plus 1, 0 over square root 2. And we are applying a C naught where the first is control and second is target. And therefore 0, 0 is not affected because the first qubit is 0. But 1, 0 is affected because the first qubit is a 1. This means I should apply a NOT gate on the second qubit. And this becomes a 1, 1. So this is how I got this quantum state. And you can also see this through matrix vector representation. Now, going back to my previous question, there are some answers. And the answer says it will be like there are 2 answers and you say 0. And this is correct. So, since this is our quantum state, check this. If Asya observes a 0, then there is no possibility that Babis can observe a 1. Why? Because if Asya is observing a 0, this means we are now in this quantum state. There is no quantum state here with non-zero amplitude, like 0, 1. If Asya is observing a 0, this means Balvis should also observe a 0. And similarly, if Asya observes a 1, this means Balvis should also observe a 1 because there is no other possibility. And when Asya makes a measurement, with 1 over 2 probability, she observes a 0, and with probability 1 over 2, she observes a 1. And once she makes this measurement, also the outcome of the measurement that will be done by Balvis, this is also determined. And this is like immediate. So once Asya makes the measurement, it's certain what Balvis will get. And this is what is called entanglement. So we cannot think about the quantum states of the two qubits independently. They are like entangled. So they are correlated to each other. And it's not like this is something predetermined. It's happening at the moment Alcia is making the measurement. At that moment, the quantum state is collapsing to either 0 or 1. So this is not something we have a classical analog. We can't have we can have correlation classically, but this is something really different, which is not existing in classical systems. Because this quantum state collapsing to 0 or collapsing to 1, this is happening at the moment Asya is making the measurement. But also be careful that this is not saying that we are sending information faster than light or something like this. We are not sending any information. Asya is not sending some information because she cannot determine whether her quantum state her qubit will collapse to 0 or 1. She's just making a measurement and randomly her state is collapsing to 0 or 1 with probability 1 over 2. And then also Balvis will observe the same state if he makes a measurement. And the converse will be also true, of course. If Balvis makes the first measurement, then this will determine Asya's outcome. And this is what we call entanglement. Actually, Balvis' qubit is also collapsed because after Asya makes the measurement, by probability 1, it will be in that state. It's no longer in superposition of 0 and 1. And mathematically, such entangled states, like the one we have 0 here, 0, 0 plus 1, 1, you cannot write the state as tensor product of two quantum states. So if you try to separate this now into two, like this is an easy exercise you can try. Take two vectors, which has two entries, and take the tensor product. It's not possible to get this vector. So you cannot express the state of this quantum system separately. You should think about all four states together. And in such a case, we say that the system is entangled. And this is not the only entangled state, of course. This is something special called Bell state. There are 4 Bell states, and this is one of them. And the others are 0, 0, minus 1, 1, minus 0, 0, plus 1, 1, and so on. And we have 0, 1, plus 1, 0, 0, 1, minus 1, 0. And in those cases, I can show it maybe from here. But maybe it was in the previous one. Okay, let me try to write it here. For instance, this is also an entangled state. 0, 1, plus 1, 0. Now let me ask you a question. Suppose this is the quantum state, and we measure the first qubit and we observe a 0. Then what is the second qubit state? Yes, it will be 1. Why? Because there is no other option. If the first qubit is in state 0, then second qubit state is 1. This is like a fully entangled state, but it could be also something like this. There is some entanglement in the system, but it's not that 2 qubits are fully entangled. Why? Because if we measure the first qubit and it's a 0, then second qubit can be in state 0 or 1. But if you make a measurement and first qubit is in state 1, then for sure you know that your second qubit should be in state 0. So there is some entanglement, but it's not like the one we have here. But I just want to give you the idea that, so this is not the only entangled state. There can be some other entangled states. Any questions? Now we will see a protocol for sending information, sending classical information using entangled qubits. So if you have, I forgot to add one thing. This effect of like measuring one qubit and then you know the result of the other qubit, this happens regardless of the distance between those 2 qubits. So the second qubit can be, I don't know, like in the space, and this is still true. And there's some experimental work going on for this. But now suppose that you have 2 qubits which are entangled, and now suppose that they're separated. Asya has one of the qubits and Balvis has one of the qubits, those entangled qubits. They didn't measure it yet. They're entangled. Now using those 2 qubits, we will send some information. Now they're separated and they want to send some classical information. By classical information, I mean a message like 00, maybe 01, 2 bits of, we will send 2 bits of classical information. We will send either the message 0001, 10, or 11. Suppose this means A, B, C, D. I don't know, like we would like to send some message. We encode it using 2 digits, 0001, 10, or 11. So we will send a classical message. Now, this is how the protocol works. So Asya is the sender, Balvis is the receiver. Asya chooses what to send as the message. Okay, so it's either 0001, 10, or 11. And depending on the message, she applies some operation on her qubit. So if she would like to send 10, then she applies a Z gate on her first qubit. If the message she would like to send is 11, then she applies both Z and NOT gate on her qubit. So depending on what her message is, she is applying some operations on her qubit, and then she's sending her qubit to Balvis. So we have quantum communication here. To send a message, we are sending a qubit. And once Asya sends her qubit, then Balvis has now 2 qubits. And he applies a control NOT. And then other one. So overall, this is how the protocol looks like. Asya has her own qubit, Balvis has his own qubit, they're entangled to start with. And then Asya is kind of doing an encoding by applying either like the Z or NOT operator, or maybe both. So depending on the message she wants to send, she is applying something on her qubit, and then she's sending her qubit to Balvis, and Balvis now has the 2 qubits, and he is applying C0 and Adaman. And then he is making a measurement. And as a result of this, after making the measurement, Balvis is going to read what Asya wants to send her. Exactly. Like if Asya wants to send 0, 0, Balvis will read 0, 0 here. So now he has 2 qubits and he makes a measurement, he will get 2 bits of information. And what happens here? Asya can send 2 bits of classical information by sending a single qubit. Okay, you may say like there are 2 qubits involved in this protocol, but what's sent from Asya to Balvis, it's only a single qubit. And by sending single qubit, she's sending 2 bits of information, actually. And this information is encoded. I mean, if someone steals the qubit, they cannot know what Asya is sending because they also need Balvis qubit. Why this is true? You can trace this by performing the mathematical operations. Maybe I can, let me check if I have it here. I think this is left as an exercise here. Yes. There is one of the cases here. We can check. Let me first check the questions. Are the entanglement requirements Adamart gate and then not gate? Yes, you can apply more gates. You will be still in entangled state. Actually, here C0 is the key thing because this is a gate which is acting on 2 qubits. And to entangle qubits, you need a gate like C0, which is applying on more than 1 qubit. So to get this best states, yes, you need Adamar and C0. And you could have like Z and X as well. Still, you will be in an entangled state. Step before the encoding, is it like key exchange? Is it an initialization step in classical cryptographic system? The step, if you are asking about this part, um, if you're asking about this part, this is just creation of the entanglement. If you are asking about this part, this is Asya's way of encoding her message. Yes, this is entanglement creation. So to start with, you need entangled states. In reality, how this is performed, for instance, in photonic systems, as far as I know, they create entangled pair of photons. They have those special devices to create entangled pairs of photons. Why we need entanglement? Because without entanglement, if you do the maths, you will see that the output is not what you want. So thanks to entanglement, you can do this protocol. And you can do many other protocols thanks to this entanglement. By the way, we are running kind of out of time. I will also need to leave. Therefore, here there is a worked example for the cases where the message we would like to send is 0, 0, and 0, 1. But I will share this in Discord so you can check the maths. So I will not right now go into detail, but I will move on to teleportation. But I will answer your questions, of course. You are right. We are using 2 quantum bits in total, but we are sending single qubits. So this is what we count here. We are sending 1 qubit instead of sending 2 classical bits. But yes, overall, the protocol is requiring 2 qubits. If we need to entangle qubits to start it, but when the message is sent, the quantum state, yes, it collapses. Yes, this is like a one-time messaging opportunity. with one pair of qubits, you can send 2 bits of information. If you look in that sense, yes, then there is no advantage. But there is the advantage that there is no way of stealing the information. Of course, someone can enter and modify the message. If Asya's qubit is modified, then the message sent will be different. This is possible. But you cannot enter and like steal the qubit Asya sending. If you steal the qubit, this will not be useful for you without getting also the second qubit, which Balvis has. You may think of this as an advantage of this protocol compared to classical protocols. Now, I will talk about another protocol, which is quantum teleportation. And this protocol is about sending a quantum state. So imagine you have a qubit, and you would like to send this qubit to someone else. You would like to send the information stored inside this qubit. Let's say your quantum state is A and B. And you would like to send this information. First of all, it can be that you don't know what is inside the qubit. You don't know the A and B information. Then there is no way to get this unless you have multiple copies of this, because how can you know if it is A or B? You cannot know this. In such a case, if you can send this to, if you would like to send this to someone else, this is a protocol you can use. And also, again, this might be used for like secure communication. But the important thing here is we are not teleporting something physical, or this is sometimes like misused, the word teleportation. Here we are sending kind of information. We are sending the quantum state actually. And for this protocol, we will use 3 qubits. The first one is the message we would like to send. I mean, this quantum state we would like to send, basically. This is quantum state AB, vector AB. And then we have 2 more qubits. And the first one is Asya's qubit, second one is Balvis qubit, and those are entangled. So if we write the state of the system we have currently, it's this one. So this is the state of the first qubit, A0 plus ACAT 0 plus BCAT 1. And this is the entangled qubits. And we will say this is Q2, and this is Q1, and this is Q0. So we have 3 qubits. And this is the current quantum state. Any questions about this, either in the maths or in the concept? Any questions? Okay. Yes, I can repeat, of course. Q2, first qubit is the quantum state Asya would like to send. So this is Q2. This is A0 plus B1. Then Asya and Balvis, they share 2 qubits. They are entangled. Those Q1 and Q0, they are entangled. Asya has Q1 and Balvis has Q0. So this is Q1. I cannot write it, but like this is Q1 and this is Q0. And this is Q1 and this is Q0. But since this is entangled, I cannot separate the state. So overall, this is Q2 and this is the quantum state of Q1 and Q0. So those are the 3 qubits we have. Is it okay? Okay. Now, this is how the protocol will work. First, Asya will apply C0 on her qubits. So the first two are Asya's qubit, and Q2 will be the control, and Q1 will be the target. And what will be the new state? So remember C naught. If first qubit is 0, nothing is changing. If first qubit is 1, then the second qubit, on the second qubit we have not. So this is the same. This will stay the same. But here this will be 1, 1, 0. And this will become 1, 0, and 1. Now let's see this here. So after applying C naught, this will be the new quantum state. So this was the state before C naught. This is the new state after Asya applied C naught. Any questions? Okay. If there are no questions, then what is the next step in the protocol? The next step in the protocol is that Asya will apply Adamar on Q2, on the qubit he would like to send. Now, let's see how it will transform our state from this into this one. Okay, this is the state before Adamar. The state written here. Now we are going to apply Adamar on the first qubit. And I think I had like an easier explanation here, which I will use. Okay, so it's the same. Just instead of A and B here we have alpha and beta, but otherwise it's the same. So we would like to apply Adamar on the first qubit. On this one, this one. So those are the first qubits. I mean, we have a single first qubit, but you know, like we are in superposition. So what happens mathematically if we apply Adamar to first qubit? So this 0 becomes 0 plus 1 over square root 2. Therefore, it is like we have plus state tensored with 0, 0. So this becomes 0, 0, 0 plus 1, 0, 0. Similarly, this becomes 0, 1, 1 plus 1, 1, 1. Why? Because this is 0 plus 1 plus state. So it is 0 plus 1. And now we are tensoring this with 0, 0. So it becomes 0, 0, 0 plus 1, 0, 0. Same goes here. This becomes 0, 1, 1 plus 1, 1, 1. And since this is 1, this becomes 0 minus 1. Be careful. So therefore we have 0, 1, 0 minus 1, 1, 0 because we have a minus sign here. And this becomes 0, 0, 1 minus 1, 0, 1. Any questions? Or is it fine? Okay. Why the negative sign? So this is the quantum state 1. And when you apply Adamar on quantum state 1, then what you get, remember, is 0 minus 1 over square root 2. Therefore, here we are tensoring 0 minus 1 over square root 2 with 1, 0 and 0, 1. So instead of a plus, here we have a minus. And this is where this minus sign comes from. Okay. Then we just write this quantum state like this. We just take out the common product. So we write it as like, we separate the state of the first two qubits. So first two qubits and the third qubit. So what are here, what we have with 0, 0, we have 0, 0 alpha 0. And here, check here, we have beta 1. And here we have 0, 1, 1, and let's see, we have 0, 1, 0. So we are just expressing the same thing, but we are just separating the first two qubit states. So we are taking like the common parentheses outside. Just mathematical modifications, algebraic modifications. Any questions from moving to this state, from moving here to here? And why we would like to separate the first two qubit state from the third qubit state? Because the first qubits are Asya's qubit and the last qubit is Balvis qubit, remember. And now at this stage, if you look at this quantum state, you can see what Asya will observe if she makes a measurement, right? For instance, what is the probability that she will observe 0, 1? Can you tell this? One over 4, right? So all states have equal probability right now. If Asya measures her own qubits, the two qubits, then with probability 1 over 4, she will observe 0, 0. With probability 1 over 4, she will observe 0, 1. She will observe 1, 0 or 1, 1. Can everybody see this? Or do you have any questions? Check first two qubits. Here, 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 and here. Asya's two qubits is an equal superposition of all four possible states. Any questions about this? No? Okay. Then let me ask you another question. Now, suppose that Asya observes 0, 1. What happens to Balvis qubit? What is the quantum state of Balvis qubit? Can you write it? Let me repeat my question. Asya makes the measurement and she observes 0, 1. Then what is the quantum state of Balvis's qubit? But Balvis did not make the measurement yet. Let me try to express my question again, because I'm not asking about a number or a probability. Here is my question. Okay, suppose that Asya makes the measurement and she observes 0, 1. And if this is the case, I'm asking, what is the quantum state of Balvis's qubit? Is Balvis's qubit is it in state 0, Is it in state 1? Is it in equal superposition of 0, 1? Or is it in alpha 0 plus beta 1? So what is the quantum state of Balvis's qubit if Asya is measuring 0, 1? Okay, now we have some answers. Nice. And the answers are correct. Balvis's qubit will be in this state, which is beta 0 plus alpha 1. Is this clear to everyone, or do you have any doubts, any questions? And if you are able to see this, then you will also see that if Asya makes the measurement and she sees 1, 0, then this is Balvis's qubit state, and so on. And for instance, if Asya makes the measurement and she observes 0, 0, then check this quantum state. This is exactly the quantum state Asya wanted to send to Balvis. So if Asya makes the measurement and if she observes 0, 0, then Balvis exactly gets the quantum state Asya wanted to send. Balvis ends up with the quantum state Asya wanted to send, while Asya loses this quantum state. She no longer has access to this quantum state, alpha 0 plus beta 1. So we kind of destroyed the quantum state Asya had, but now we form the same quantum state Balvis, in Balvis's qubit. And so we sent the quantum state. Chemical revision of the previous circuit to send quantum. It's really similar, actually, because the operations we are performing are also similar. There we were sending classical information, now we are sending quantum state. They are really similar. But actually, we are not done. So the protocol says, okay, Asya should make the measurement, but then we need something more. Why? Because if Asya observes 0, 0, then this is perfect. Well, this got the state. But if Asya observes 0, 1, then this quantum state is not exactly the state Asya wanted to send. But it's the same quantum state with amplitude of 0 and 1 flipped. Can you see this? Asya wanted to send alpha 0 plus beta 1. But Balvis has beta 0 plus alpha 1. Therefore, in this protocol, Asya also needs to send the measurement results. She makes the measurement results, and then she tells Balvis, hey, Balvis, I got 0, 1. And then Balvis knows that he needs to apply some more operation to get the exact quantum state. For instance, in this case, Balvis needs to apply an X gate. Because if he applies an X gate, then he will exactly get alpha 0 plus beta 1. And if Asya gets 1, 0, Asya tells Balvis, hey, Balvis, I got 1, 0. Then Balvis applies a Z gate. So that this becomes alpha 0 plus beta 1. Therefore, in this protocol, we also need to send 2 bits of classical information. Hence, again, this is not faster than speed of light because we also need to send some classical information. But overall, let's think about what we did. Asya wants to send a qubit, a quantum information, and Asya and Balvis share entangled pair of qubits. And to send this quantum state, she used some quantum operators and plus she sent 2 bits of classical information. And at the end of this protocol, based on the information sent by Asya, based on the classical information sent by Asya, Dalvis applied some operators and he gets the qubit Asya wanted to send. Do you have any questions? I will also share this document I'm sharing right now with you. But you can also find the same in the notebook. And there's also like tasks so that you can really code and see this. And it will be really great if you can do this so that you will understand what's going on. Okay then. If there are no questions, we can end for today. Thanks for joining and listening. Um, you can always write in Discord if you have any questions. I will also share the links. So
On
thanks
behalf
again.
On behalf of NCC Turkey, I would like to also thank Özlem Hocam for this interactive presentation, and I would like to thank all attendees for their active participation. I guess we can end the training for today, right? And see you then.
Thank you. See you.